July 5th, 1943, 0600 hours. The ground north of Belgorod shakes with the opening of the largest armored offensive Germany ever launched on the Eastern Front. Hundreds of tanks move forward through morning haze, preceded by artillery that has been pounding Soviet positions since before dawn. Leading the 48th Panzer Corps' assault on the southern face of the Kursk salient is the Gross Deutschland Division, one of the finest armored formations the Wehrmacht possessed, built around the brand-new Panther tank that Hitler had personally delayed the entire offensive to put into the field. On this day, Gross Deutschland has 118 tanks. Among them are Panthers fresh from the factory, and there is real expectation in the German command that today, finally, the tide will begin to turn. The left flank of Gross Deutschland's advance hits a Soviet minefield shortly after the assault begins. Within hours, 36 Panthers are immobilized, not knocked out by gunfire, not destroyed by air attack, stopped cold by objects buried in the dirt, objects made largely of wood, containing less than half a kilogram of TNT each, that cost almost nothing to produce and were installed not by soldiers with specialized training but by engineers working through the night alongside conscripted civilians in the weeks before the battle. By evening on July 5th, 48th Panzer Corps reports it has 38 Panthers operational. It had started that morning with 240 kilometers to the north on the other face of the salient. The situation is more immediate and more dramatic. The German Ninth Army's attack runs directly into the deepest minefield concentration in the entire defensive system. The 653rd Heavy Panzerjäger Battalion begins the day with 49 Ferdinand self-propelled guns, the 65-ton behemoths that Germany's engineers had built around a gun powerful enough to defeat any Soviet tank at combat range. By 1700 on July 5th, 37 of those 49 Ferdinands have been lost in the minefields. The battalion commander Hauptmann Spielmann is wounded not by enemy fire but by a Soviet anti-personnel mine while he is dismounted from his vehicle and guiding his driver through the debris. Command passes to Oberleutnant Helmut Ulbricht. With 12 operational Ferdinands remaining, the battalion reaches its first day objective 12 hours behind schedule. This is what Soviet landmine doctrine achieved on the first day of the Battle of Kursk. Not through a single decisive engagement, but through geometry, through the mathematical reality of 503,993 anti-tank mines and 439,348 anti-personnel mines, distributed across a defensive belt that the Wikipedia article on the battle, drawing on official Soviet and German records, states achieved densities of 2,500 anti-personnel and 2,200 anti-tank mines per kilometer in its most critical sectors. That is 6 times the density used in the defense of Moscow, 6 times the concentration that had stopped the Wehrmacht 2 years earlier when Germany was at the height of its power and the Soviet Union was fighting for its existence. To understand how the Soviet Union arrived at a mine doctrine of this precision and this scale, you need to start not with the weapons themselves but with the strategic situation that made them the only rational choice. By the spring of 1943, the war on the Eastern Front had reached a kind of equilibrium that both sides knew was temporary. Stalingrad had destroyed the German 6th Army and shattered the myth of Wehrmacht invincibility, but Germany still possessed enormous armored strength, and both Zhukov and the German commanders understood that the summer of 1943 would be decisive. The Kursk salient, a bulge in the front line roughly 250 kilometers wide and 160 kilometers deep, was the obvious German target. An attack from north and south could, in theory, cut off and destroy the massive Soviet forces inside it. German operational planners saw it. Soviet intelligence confirmed it through multiple channels, including, as historians have documented, information from British codebreakers at Bletchley Park. What happened next is the decision that made Kursk the battle it was. At a Stavka meeting on April 12, 1943, Marshal Georgy Zhukov argued against a Soviet preemptive strike and in favor of something harder to accept: deliberate waiting. let the Germans attack into prepared defenses, exhaust themselves against fortifications they could see being built and could not stop, and then strike with fresh reserves when the German armor had bled itself white against concrete and steel and earth. The argument required confidence that the defenses could absorb what Germany intended to deliver. The key to that confidence was the minefield. The Soviet approach to mine warfare at Kursk was not improvised. It was the culmination of doctrinal development that had been underway since 1941, informed by bitter experience of what happened when tank armies were allowed to advance unimpeded. Soviet engineers had learned that a tank stopped by a mine is, in crucial military terms, almost as useful a kill as a tank destroyed by a shell. A mine hit typically damages the running gear, tracks blown, road wheels destroyed. Sometimes the hull penetrated through the belly if the charge is large enough and the vehicle unlucky enough to detonate directly over it. The tank stops. Its crew must decide whether to stay inside an immobilized vehicle under fire or dismount and become infantry. Either way, the tank is out of the battle until recovery vehicles can reach it, and recovery vehicles are themselves targets. On a battlefield as dense with mines as Kursk, recovery was not simply a logistical matter. It was a combat operation. The weapons themselves that went into the ground across the Kursk salient represent a deliberate engineering philosophy that chose reliability and producibility over sophistication. The TMD-40 was a wooden-cased anti-tank mine, a rectangular box containing blocks of TNT totaling 3.2 kilograms of explosive. With a simple lever mechanism under the lid, downward pressure pulled a retaining pin from the fuse, releasing the striker. Its activation threshold ran between 80 and 250 kilograms, depending on source and configuration, well below what any tank's hull would exert, well above what a soldier's foot would apply. The wooden case meant almost no metallic signature. The 1940s mine detectors available to German engineers were magnetic induction devices that worked by detecting disturbances in the electromagnetic field caused by ferrous metal. A box made of pine planks and TNT blocks interrupted nothing they could measure. German sappers had to probe for these mines with rods, one push of the probe at a time, in ground that might also contain the weapon we're going to spend most of this script examining. The PMD-6 is, by any aesthetic standard, the least impressive weapon of the Second World War. It is a wooden box 190 millimeters long, 90 millimeters wide, and 65 millimeters tall. The lid is hinged, with a slot cut into it. Inside sits a 200-gram block of TNT and a MOV series fuse. The entire assembly weighs 400 grams. Activation pressure runs between 1 and 10 kilograms. The lighter end of that range activates under the weight of a grown man's foot. The heavier end requires a firm step. There is nothing in this weapon that required a machinist, a foundry, a metal press, or any industrial process beyond cutting wood and assembling components that a moderately skilled worker could handle at a bench. The Wikipedia article on the PMD series mines confirms that it has a relatively short lifetime because the wood is vulnerable to rotting and splitting, but in dry conditions these mines were found operational up to 10 years after being laid, and unlike the TMD-40's anti-tank purpose, the PMD-6 is explicitly an anti-personnel weapon. Its 200-gram TNT charge is not designed to damage a tank. It is designed to injure or kill the engineer who comes forward with a probe to find the anti-tank mines hidden alongside it. This is the integrated system. You cannot understand what happened to the 653rd Panzer Jaeger Battalion's Ferdinands on July 5th without understanding the relationship between the PMD-6 and the larger mines surrounding it. When German engineers approached a Soviet minefield to clear lanes for the advancing armor, they faced not just the task of locating anti-tank mines with probes, already a slow, dangerous operation under fire, but the near certainty that the anti-personnel mines seeded throughout the same ground would injure anyone who moved through it on foot. Hauptmann Spielmann was not an unlucky commander who happened to step on something by accident. He was a man attempting to do exactly what his situation demanded: get out of his vehicle and guide his driver through ground his driver could not navigate safely from inside, and the anti-personnel mine that wounded him was exactly where it was supposed to be. The system was working as designed. The POMZ stake mine completed the defensive trinity, where the TMD-40 and the wooden box mines required direct weight to activate. The POMZ was a cast-iron fragmentation body mounted on a wooden stake, connected by a tripwire to a MUV series pull fuse. The sappers.com.ua technical documentation for the POMZ-2 describes the deployment method precisely. A wooden stake is driven into the ground, the mine body mounted on it approximately 30 centimeters above the surface, and a tripwire tensioned between the mine's release pin and a second stake 4 meters away. The tripwire could be set at shin or ankle height in vegetation, almost invisible. When a soldier's leg catches the wire and pulls the release pin, the MUV striker fires the detonator. The Wikipedia article on the POMZ series notes that the crude fragmentation jacket produces an uneven fragmentation effect, with an effective radius quoted at 4 meters, though large fragments may travel considerably farther. The mine was not intended to provide clean, uniform lethality. It was intended to wound at least one man in a patrol or clearance team and make every man behind him hesitate before the next step. Before we get to the specific numbers from July 5th and what they mean in cold strategic terms, if this level of forensic detail is what you watch this channel for, subscribe. It takes seconds, and it means the channel can keep doing the primary source work that makes content like this possible. Let's talk about what the Germans faced when Operation Citadel actually began. The preparation of the Kursk defenses involved a mobilization of human labor that dwarfs almost anything in the war's history, outside of the construction of entire cities. The Wikipedia article on the battle records that the Soviets employed the labor of over 300,000 civilians. These were not volunteers in any meaningful sense. They were men, women, and older children from the surrounding villages and towns who were directed to the front and handed tools. They dug more than 9,200 kilometers of trenches across both fronts, the equivalent of digging a trench from Moscow to London and back again. They built 686 bridges, constructed 2,000 kilometers of roads, and they helped lay the mines. Hundreds of thousands of mines placed by hand, one at a time, in patterns determined by Soviet engineers who had calculated where German armor would most likely attempt to pass. The Dupuy Institute analysis of the mine deployments at Kursk, drawn from Christopher A. Lawrence's research in his 1,600-page study of the battle, provides the most granular data on what the 1st Defensive Echelon actually contained. In the 6th Guards Army sector alone, by July 4th, there were 88,261 anti-tank mines and 53,324 anti-personnel mines in the 1st Echelon, with 80% of the total mine load concentrated in that forward belt, across the entire 1st Defensive Echelon of the Voronezh Front's position, the zone that German armor would hit first on the southern face. There were at least 221,846 anti-tank mines and 219,134 anti-personnel mines in place before the battle began. The linear density across the 175 kilometers of front in this sector comes out, in the Dupuy Institute's calculation, to approximately 1,267 anti-tank mines and 1,251 anti-personnel mines per kilometer. In the highest density sectors, as the HistoryNet account of the battle records, a single morning's advance ran into 36 Panthers being immobilized on Grossdeutschland's left flank before their crews had fired more than a few rounds. The Dupuy Institute's Mines at Kursk series also addresses the question that this video's title is built around. How did mine casualties compare to everything else? Lawrence's research places the number of German tanks lost to mines on July 5th alone in the range of 131 to 154. This amounts in his analysis to 62% of German tank losses on that day, and accounted for 10% of total German tank losses across the entire battle from July 4th to 18th. Vasily Zamolin's Demolishing the Myth, cited in the Dupuy Institute's analysis, contains an observation that sounds almost paradoxical until you think it through. It required 350 to 400 anti-tank mines on average to damage or destroy one tank in front of the defensive lines, but in the depths of the defense where mine placement occurred along lines of advance already revealed by the enemy, that number fell to 150 to 200 mines per tank. The mine was not a precision weapon, it was a probabilistic one. You did not aim a minefield at a tank. You created a field dense enough that any tank crossing it would eventually strike one, and then you covered the field with fire so that the delay imposed by the mine, the immobilization, the recovery operation, the time spent probing and clearing lanes, happened under conditions where the standing still was as dangerous as the mine itself. The New World Encyclopedia's account of the battle includes what may be the single most representative data point of the entire engagement. Mobile obstacle detachments, small groups of Soviet engineers tasked specifically with rapid mine laying, emplaced over 90,000 additional mines during the battle itself, working at night, laying fresh minefields immediately in front of German advanced positions. This was not static defense. This was a living, adaptive system that watched where the Germans pushed and put mines there before they pushed again. On a front where the deepest German penetration in the south reached roughly 35 kilometers before the offensive stalled, these mobile detachments were closing off the routes being used while the Germans were still trying to use them. The German response to the minefields deserves examination because it illustrates not just the tactical problem but the fundamental impossibility of the situation Germany had created for itself. Standard German mine-clearing doctrine involved combat engineers moving forward with probes and detectors to identify mines, mark them, and either remove them or create bypass routes for the following armor. This was slow work under optimal conditions, perhaps a few meters per minute in a dense field. Under fire with artillery targeting the clearance teams, it became not just slow, but catastrophic. The New World Encyclopedia's battle account notes that even when vehicles successfully cleared mines, there was no reliable onboard marking system to show following tanks where the cleared lanes were. The 313th radio-controlled Panzer Company lost 4 Borgwood remote-controlled demolition vehicles, the specialized engineering machines Germany had brought specifically to deal with Soviet minefields, when one of its platoons drove across an uncharted, friendly minefield during approach. The weapons designed to breach the minefields were themselves destroyed by minefields. Germany tried to use radio-controlled explosive carriers to blast lanes through the Soviet positions. The terrain was too heavily mined for even these to operate reliably. The Ferdinand provides the most concentrated illustration of what the minefields achieved. The Ferdinand, redesignated Elephant after the battle, was Germany's heaviest and most powerfully armed tank destroyer, built on the chassis of Ferdinand Porsche's rejected Tiger design and mounting an 88mm gun capable of defeating any Soviet armor at battle range. It weighed 65 tons. It could, in theory, absorb enormous punishment from Soviet anti-tank weapons. What it could not do was avoid mines it could not see, and what its crew could not do was remain inside it when it had been immobilized in a minefield under artillery fire. The weaponsandwarhistory.org account of the Ferdinand at Kursk contains the specific sequence. The barren terrain was very heavily mined. The radio-controlled explosive carriers employed to clear it were unable to accomplish the task, and the battalion made very slow progress through the minefield with many vehicles immobilized by broken tracks and damaged idler arms. Hauptmann Spielmann dismounted to guide his driver and was severely wounded by a Russian anti-personnel mine. By 1700, with 12 Ferdinands operational and 37 lost to the field, the battalion reached its objective. The objective it was supposed to reach by mid-morning. That timing matters more than any individual casualty figure. The entire logic of Operation Citadel depended on speed. Germany needed to penetrate the Soviet defensive belts before Soviet strategic reserves could be committed, encircle the salient, and present the Red Army with an encirclement it could not break out of. The delay imposed by the minefields was not just a tactical setback for units like the 653rd or the Großdeutschland. It was the mechanism by which the strategic concept failed. Every hour that armored units spent in minefields rather than advancing was an hour in which Zhukov's steppe front, held in reserve east of the salient, specifically to counterattack after the German offensive had exhausted itself, remained intact and fresh. The mines did not need to destroy Germany's tanks. They needed to slow Germany's tanks long enough for Soviet reserves to arrive. This they achieved comprehensively. The comparative cost picture is not a minor footnote. It is the central economic argument for why the Soviet approach was correct. The German Landmine 35, Germany's primary anti-tank mine, was a steel-cased device containing 5.5 kilograms of TNT, weighing over 9 kilograms, and requiring sheet metal pressing, precision fuse manufacture, and machining to produce. Germany made 3.6 million Landmine 43s between March 1943 and the end of the war, a substantial production run by any measure, but one that consumed enormous metal and machine time. The Soviet TMD-40 was a wooden box. The PMD-6 was a smaller wooden box. Neither required metal beyond the fuse components. Both could be produced in facilities with no heavy industrial equipment. The raw material for the casing came from lumber. The explosive filling came from TNT blocks that the same facilities producing artillery shells and bombs were already manufacturing as a standard output. The Dupuy Institute's analysis of the battle makes a point that should be read carefully. Soviet engineers laid more than 500,000 anti-tank mines and nearly 440,000 anti-personnel mines at Kursk. The total number of mines across all defensive belts approached 1 million. A German Tiger tank cost approximately 800,000 Reichsmarks to produce and required months of manufacturing time. A wooden box mine cost a fraction of a Reichsmark's worth of materials and could be made in minutes. The exchange ratio that Germany walked into was not just unfavorable in isolation, it was structurally ruinous. Germany was gambling its finest armored formations against a weapon its enemies could produce faster than it could replace what it lost. The mobile obstacle detachments that operated during the battle itself represent a doctrinal refinement that is worth examining separately from the prepared defenses. These were small, fast-moving engineer teams, typically moving at night, carrying mines and minimal equipment, whose specific mission was adaptive mine laying in response to German advances. When German forces pushed through or around a prepared minefield and began developing a line of advance, these teams would be directed to that line overnight. By morning, what had been open ground the Germans were exploiting was seeded with mines. The New World Encyclopedia account puts 90,000 additional mines laid this way during the battle. That is roughly 1/6 of the entire pre-battle mine deployment, added in real time as the Germans moved. The Dupuy Institute notes the analytical implication of this. The mines placed in the depths of the defense along revealed lines of advance achieved higher per-mine effectiveness. 150 to 200 mines per tank disabled, rather than 350 to 400. Precisely because these teams were placing mines where tanks were actually going rather than where tanks might go. The Grossdeutschland Division's trajectory through the battle illustrates what this cumulative effect looked like at the formation level. On the morning of July 5th, the division had 118 tanks. After 5 days of fighting, by July 10th, it reported 3 Tigers, 6 Panthers, and 11 Panzer III and 4 tanks operational. That is 20 operational vehicles out of 118, a force reduced to roughly 17% of its original strength in 5 days. The 48th Panzer Corps situation, of which Grossdeutschland was the centerpiece, showed 38 Panthers operational, with 131 awaiting repair out of the 200 it started with. Many of those 131 Panthers awaiting repair were mine casualties, vehicles with broken tracks and damaged running gear that could be fixed but that required recovery from terrain still under fire and still laced with mines. The HistoryNet account notes precisely what the first morning looked like for the Panthers. Grossdeutschland's left flank became entangled in a thick Soviet minefield, immobilizing 36 Panthers, stalling the division and rendering it vulnerable to Soviet anti-tank and artillery fire. An artillery officer in the division's own ranks noted the chaos in a journal entry recorded by historians of the battle. Everything is shrouded in dust and smoke. The barrage has moved beyond the forward trenches into the rear, and no one is certain where the infantry has gone. That last detail, losing track of where the supporting infantry has gone, captures a crucial secondary effect of the minefields that casualty figures alone do not show. German armored doctrine in 1943 understood that tanks operating without infantry support were enormously vulnerable. Infantry suppressed anti-tank gun crews, cleared buildings, covered the flanks of armored formations against close-range anti-tank weapons. When the mines stopped the tanks and the anti-personnel mines prevented infantry from moving freely through the same ground, the coordination between the two arms broke down. Tanks that could not move without infantry, who could not advance without being wounded, became stationary targets for the Soviet artillery and anti-tank guns that the defensive system positioned specifically to cover the minefield approaches. The mines were not the only weapon. They were the first weapon, the one that held the other weapons' targets in place long enough for everything else to fire. The production philosophy behind the Soviet mine arsenal at Kursk contains a lesson that military historians have continued to draw on for 80 years. The TMD-40 was discontinued in 1943 when metal supplies improved and more sophisticated designs became available, but the PMD-6 continued in service far beyond the war. The IMAUSA description of original specimens notes that in dry climates, these mines were found operational up to 10 years after laying. The POMZ stake mine spawned copies in China, East Germany, North Korea, Yugoslavia, and Vietnam, and was found in active use across dozens of conflicts through the Cold War and beyond. The Wikipedia article on the PMD series states that by the late 1990s, modern detectors could locate a PMD-6 at a range of 30 meters, but in 1943, no such detector existed. German engineers faced these weapons with the same tools that soldiers had used to find landmines for a generation: a metal probe, patience, nerve, and the hope that the anti-personnel mines mixed into the field with them would not find their hands or knees before their probe found the next anti-tank mine. The question the title of this episode poses, did the Soviet mines stop more German armor at Kursk than any gun, can be answered with the data the Dupuy Institute assembled. On July 5th, 62% of German tank losses were attributable to mines. Across the whole defensive phase of the battle, mines accounted for 10% of total German tank losses, with a significant fraction of the remaining 90% occurring to vehicles already slowed and fixed in position by mine-induced delays. The anti-tank gun cannot claim 62% of losses on the first day. The Soviet Air Force cannot. The T-34 certainly cannot. On July 5th, 1943, the weapon that did more damage to German armor than anything else was a wooden box with a block of TNT inside it, triggered by the weight of a tank that could not see it coming. The German 9th Army advanced 12 to 15 kilometers between July 5th and July 15th before its offensive effectively ended, this against a defensive position it was supposed to break in 24 hours. The 4th Panzer Army in the south made somewhat better progress, but stalled before reaching the 2nd defensive belt intact. By July 12th, when the Soviet counteroffensives began with Operation Kutuzov in the north and Operation Rumyantsev to follow in the south, the German armored strength that had begun the offensive was critically depleted, not primarily by the kind of dramatic tank versus tank combat that dominates popular memory of Kursk, but by the slow, grinding attrition of minefields that forced tanks to stop, forced engineers into fire to clear them, forced commanders out of their vehicles to guide their drivers, and forced recovery teams to operate under artillery that specifically targeted them. Returned to 1700 on July 5th, 1943. The 653rd Panzer Jaeger Battalion has 12 Ferdinands operational. Hauptmann Spielmann has been evacuated with mine injuries. The battalion has reached its first day objective approximately 12 hours after it was supposed to. Behind it in the minefield, 37 Ferdinands sit waiting for recovery vehicles that will themselves need to navigate the same ground. Those vehicles will need engineers in front of them. Those engineers will have probes in their hands, and no way of knowing whether the next push of the rod will find wood or dirt. Zhukov argued in April that the Germans would break their teeth on Soviet fortifications. He was right in the most literal sense, and the tool that broke those teeth first, before the guns could fire, before the reserves could commit, before any of the dramatic tank engagements that history remembers, was a wooden box containing 200 grams of TNT that any sawmill could produce and any conscripted civilian could lay in the dark. That is the Soviet landmine at Kursk, not Crude, perfectly calibrated,